Hello everyone, I'm Imanshu Asnani from Department of Mechanical Engineering and I will discuss material science. Subject code is ME207, unit number 5 in the series, lecture number 33, and today's topic are particle and fiber reinforced composites. So, our learning objective for today's lecture is to provide the students with a basic understanding of particle and fiber reinforced composites. And our learning outcome after today's lecture will be students have learned the basics of particle and fiber reinforced composites. Students understood particle and fiber reinforced composites in detail. So, let's start our lecture with the introduction of fiber reinforced composites. So, materials that are classified as fibers are either polycrystalline or amorphous and have small diameter. Okay, the fibrous materials are generally either polymers or ceramics. Example: the polymer aramids, the glass, the carbon, boron, aluminum oxide, and silicon carbide. You can see that these fibrous materials these are generally either polymers or ceramics. Okay. Now, on the basis of diameter and character, the fibers are grouped into three different classifications like viscous, fibers, and wires. Okay, if you take the factors like diameter and character, you can classify these fibers into different classifications like viscous, fibers, and wires. Okay, you can see the diagram here. So the whiskers, these are very thin single crystals that have extremely large diameter to length to diameter ratio. Okay, these have extremely large length to diameter ratios. So as a consequence of their small size, they have high degree of crystalline perfection and are virtually flaw free, which accounts for their exceptionally high strength. They are among the strongest known materials. Okay, these whiskers you can see in the diagram in the middle. Okay, so when you talk about whiskers, you can this the whiskers are very thin single crystals that have been extremely large length to diameter ratio. So as a consequence of this small size, they have high degree of crystalline perfection and are virtually flaw-free, which accounts for their exceptionally high strength. They are among the strongest known materials. So in spite of these high strengths, these whiskers are not utilized extensively as a reinforced medium because they are extremely expensive. Due to the high cost, these whiskers are extensively used. Okay. Now, moreover, it is difficult and often impractical to incorporate whiskers into a matrix. Okay, it is often impractical to, we can say, incorporate matrix in whiskers into a matrix. So, whisker materials include graphite, silicon carbide, silicon nitride, and aluminum oxide. Some examples of whisker materials are like silicon nitride and aluminum oxide, graphite, silicon carbide. So, fibers. Okay, the fibers are also very important. Now, fibers are either polycrystalline or amorphous and have a small diameters. Fibrous materials, these are generally either polymers or ceramics. Example, the polymer aramids, the glass, the carbon, boron, aluminum oxide, and silicon carbide. Okay, when we talk about fibers, you can see these fibers, these are either polycrystalline or amorphous. Okay, we talk about these fibers, you can see the fibers in this diagram on the right hand side having short fibers and this continuous fibers. So you can see these fibers, these are either polycrystalline or amorphous and have small diameters. And fibrous materials, these are generally polymers or ceramics. So fine wires that have relatively large diameters, typically materials include steel, molybdenum, and tungsten. Okay, so these wires are utilized as a Radial steel reinforcement. What do you the name technical name is? Radial steel reinforcement in automobile tires. Okay, you use this kind of wires in as a radial steel reinforcement in automobile tires, in filament wound rocket casings, and in wire wound high pressure hoses. So you can see this fine wires have a wide applications. First, they have relatively large diameters, and these typical materials, including like steel, molybdenum, and tungsten, these are there. Okay, so many of the modern technologies require materials with unusual combination of properties. Okay, many of these modern technologies, they require materials with unusual combination of properties that cannot be met by the metal. So conventional metallic alloys, I repeat, conventional metallic alloys, ceramics and polymer materials, example, materials needed for aerospace. Okay, now comes the applications. Okay, materials needed for aerospace, underwater and transportation applications. Okay, so for example, these engineers working in aircraft industries, these are looking and searching for structural materials. What they are doing? They are looking for structural materials that have low densities, that are strong, they are stiff, okay, they are and abrasion and impact resistant. These are not easily corroded. That is the most priority property of this in the aircraft industry. That the materials, okay, that you are searching, that structural materials that you are searching for aircraft, obviously these should not be easily corroded. Corroded, sorry. Okay, and they should be strong. They should be stiff. Okay, and obviously lightweight. So obviously this is a rather formidable combination of characteristics. So usually strong materials are relatively dense, also increasing the strength or stiffness generally results in a decrease in impact strength. What they say generally results in a decrease in impact strength. So therefore, in composites, the whole is greater than the sum of the parts. Okay, when we talk about in composites, the whole is greater than the sum of the parts. So wood, bamboo, corn are examples of nature's composites, where two materials combine to reinforce and bind together. You can see in the wood, you can feel that the composites are there. Okay, you can easily feel it. Okay, so they say that this wood, bamboo, and corn, these are examples of nature's composites where two materials combine to reinforce and bind together. So composites of sort which include multi-phase metals, alloys, okay, and ceramics and polymers. These include multi-phase metal alloys, ceramics and polymers. So this is rather interesting, you can say, discussion about these composites. Okay, composites of sort which include multi-phase metal alloys, ceramics and polymers. So let's discuss about composites. Okay, now you can see in the diagram how it is seen that we have a fiber. So fiber, it provides strength and stiffness like glass, carbon, aramid. These are natural fibers, and then you plus composite material matrix, which you have protects and transfers load between fibers, and then you have a fiber composite matrix, which says that it creates a material with superior property with attributes superior to either composite alone. So let's think about that. Well, what about a composite? So composite is considered to be any multi-phase material that exhibits a significant proportion. What do you call about composites? It is considered to be any multi-phase material that exhibits a significant proportion of the properties of both constituent phases, such that a better combination of properties is realized. So this is termed as principle of combined action. Now you're talking about combined action. This is really interesting when you talk about composites. Okay, so you can see this composites. You can composites is considered as a multi-phase material that exhibits a significant proportion. Okay, see, uh, they have given you a principle of combined action. So You can say that composites is considered to be any multi-phase material that exhibits a significant proportion of the properties of both constituent phases such that a better combination of properties is realized. Okay, now they have given this principle at okay, like principle of combined action. So according to this principle, the better combinations are fashioned by the judicious combination of two or more distinct materials. Okay, now a composite is a multi-phase material that is artificially made as to one that occurs naturally. So, in addition, the constituent phases in composite that must be chemically dissimilar. Okay, the constituent phases in a composite must be chemically dissimilar and separated by distinct interface. That is why most metallic alloys and many not fit this definition because their multiple phases are formed as a consequence of natural phenomena. Okay, that is why most metallic alloys and many ceramics also these do not fit into this definition because their multiphases are formed by the consequence of natural phenomena. So all composites generally have one thing in common: a matrix or a binder combined with a reinforcing material. I repeat, understand things. This thing, common, very important thing. All composites generally have one thing in common: a matrix or binder combined with reinforcing material. So obviously, a composite consists of a matrix material dispersed within which is a dispersion of one or more phases of another material. A composite consists of a matrix material. They say a composite consists of a matrix material dispersed within which is a dispersion of one or more phases of another material. So the fibers are directionally oriented. Now comes the important thing. If the fibers are directionally oriented and continuous, the material is termed as an advanced composite. Okay, this all these composites that we are studying, they generally have one thing in common. That is a matrix or binder combined with a reinforcing material. Okay, so obviously this composite consists of a matrix material dispersed within which is a dispersion of one or more phases of another material. Okay, now they are giving you another material, advanced composite. So the fibers are directionally oriented and continuous. The material is termed as an advanced composite. Now examples of composites. Okay, let's start example of composite. Okay, now you can see this in the diagram. Okay, this is just an example. Now fiber, okay, or filament reinforcement gives you high strength. High strength is there, high stiffness is there, low density is there, and then you have a matrix material, which has good shear properties and low density. But when you combine both of them to form a composite, now obviously it will give you high strength and high stiffness and good shearing properties and low density also. So you understand these properties is combined and give you a good composite material. Now some examples of composites. Okay. Now reinforced concrete is a good example of composite material. When concrete is reinforced matrix which surrounds the reinforcing fiber. Okay. What happens? When concrete is reinforced with steel rubber, the concrete becomes the matrix which surrounds the reinforcing fiber, the rubber. Another example of reinforced, you can say reinforced fiberglass products such as fishing rods, glass fibers are set in a thermostatic resin matrix. This produces a strong, lightweight, flexible fishing rod. Okay, now let's. Okay, the other fibers are produced from aramid like calver and nomex, boron, carbon, graphite, ultra high molecular weight polythene, that is called spectra. The matrix for these materials is typically a thermosetting epoxy resin. Okay, and these materials provide some exceptionally increased with the mechanical properties, sometimes 3 to 6 times greater than the steel. And repeat, these materials provide some exceptionally you can increase in mechanical properties, sometimes 3 to 6 times greater than steel. Okay, another example of composite material is a pearlitic steels. The name is pearlitic steels. The microstructure of this material consists of alternating layers of alpha ferrite and cementite. We have studied about these two terms, alpha ferrite and cementite, in iron carbon diagram. So you should know that. So the ferrite phase is so soft and ductile. The ferrite phase is so soft and ductile, whereas cementite is hard and brittle. So the combined mechanical properties or characteristics of the composite, that is pearlite, reasonably high ductility and strength. What they say, reasonably high ductility and strength are superior to those of either of the constituent phases. So the examples of composites, these are really, you can say, interesting to know. Okay, well, when I talk about reinforced concrete, you can say it is a very good example of composite material. This is what happens when matrix is reinforced in with steel rubber, the concrete becomes the matrix. It surrounds the what happens when concrete is reinforced with steel rubber, the becomes the matrix which surrounds the reinforcing fiber, the rubber. Okay, so when you talk about reinforced glass, fiberglass products, so this is another example of is the reinforced fiberglass products such as fishing rods. Okay, these glass fibers are set in a thermosetting resin matrix. So what the output is, this produces a strong, lightweight, flexible fishing rod. So you can understand that the applications are so much practical. We talk about composites. Other common varieties of composites include combinations like fiber resins, fiber ceramic, carbon metal. Okay, these combinations include fiber resins, fiber ceramic, carbon metal, metal concrete, metal resins, wood plastic. Really interesting. The varieties are too much. These include fiber resins, fiber ceramic, carbon metal, metal concrete, metal resins, wood plastic. So most of the contemporary advanced composites, I repeat, most of the contemporary advanced composites use glass, calver, modern aramid, and one of the various types of graphite fibers. Okay, what they use? Calver, glass, or one of the types of graphite fibers. So fiber composites form an important subset of this class of engineering materials. So obviously, composite, okay, is a multi-phase material that is artificially made as to one that occurs naturally. Okay, these fiber composites, they form an important subset of the class of engineering materials. And when we talk about composites, so composites is a multi-phase material that is artificially made as to one that occurs naturally. So in addition, the constituent phases in a composite, they must be chemically similar and separated by a distinct interface. Separated by a distinct interface. So that is why most metallic alloys and many ceramics, these do not fit this definition because their multiple phases are formed as a consequence of natural phenomena. Most metallic alloys and many ceramics, they do not fit this definition because their multiple phases are formed as a consequence of this natural phenomena. So you can see this in the diagram. You have a fiber material and you have a matrix material. Okay, this is how it is. Now, reasons why you are making this composites. So the incorporation of fibers into brittle ceramics, this produces composites of enhanced toughness, and fillers such as presence of aggregating concrete reduces the overall cost of the product, and additional improve the compressive strength. The second phase may furthermore be a gas as a manufacturer of foam products of low density. So on the basis of strength and stiffness alone, what to say? On the basis of strength and stiffness alone, these fiber reinforced composite materials may not be superior to metals of comparable strength. But when the specific modulus, that is the modulus per unit weight and specific strength are considered, what they say? When specific modulus and specific strength are considered, then their use implies that the weight of components can be reduced. This is an important factor in all forms of transport, where reduction of weight results in greater energy savings. Okay, so you can see that if you compare on the basis of strength and stiffness alone, fiber reinforced composite materials may not be superior to metal strength. But when the specific modulus and specific strength are considered, then their use implies that the weight of components can be reduced. So, in order to produce a new generation of extraordinary materials, scientists and engineers, while designing composite materials, have ingeniously combined various metals, ceramics, and polymers. Okay, this is the reason for making composites. Okay, that they have ingeniously combined various metals, ceramics, and polymers. Okay, no one can classify the composite materials as per simple scheme you can see in this figure. So there are three main divisions like particle reinforced, fiber reinforced, and structural composites. Okay, so we may know that there exist only two subdivisions for each main division. Like if you have composites on the upper side, then you have particle reinforced, fiber reinforced, and then structure. The structural have laminates and sandwich panels. See, structural has laminates and structure sandwich panels. And we talk about particle reinforced, you have large particle and dispersion strengthened. When we talk about fiber reinforced, then you have continuous and discontinuous. So if you talk about discontinuous, then you can have aligned, randomly oriented. This is how these classification of various composite types is done. Okay, like structure is having laminates and sandwich panels, and this particle is having large and dispersion strengthened, and then you go with the fiber reinforced, then you have continuous and discontinuous. So, and the discontinuous you have aligned and randomly aligned. So, let's start with them. The examples of these three groups include like concrete. It is having a mixture of cement and aggregate, which is a particulate composite. This concrete is having a mixture of cement and aggregate, which is a particulate composite. And you have a fiberglass, which is a mixture of glass fibers emitted in a resin matrix, which is a fiber composite. Okay, if you have a concrete, you can see that in the diagram. Because a mixture of cement and aggregate, which is a particular composite. And fiberglass also is a mixture of fiberglass embedded in a resin matrix, which is a fiber composite. And then you have plywood. Okay, alternating layers of laminate veneers, which is a laminate composite. You can see in the diagram clearly. So, the general characteristics of this composite. Okay, then let's talk about that. The composite materials are superior to these are superior to all other known structural materials and specific strength and stiffness, high temperature strength, fatigue strength, and other properties. Okay, we talk about these composite materials. Obviously, these are superior to all other known structural materials. Okay, these are superior to all other known structural materials in specific strength. Okay, in stiffness, high temperature strength, fatigue strength, and other properties. So this desired combination of properties can be tailored in advance and realized in the manufacture of particular material. Okay, so when you talk about these composite materials, obviously we can easily just have a you can say idea that composite materials are complex materials whose components differ strongly from each other in the properties, are mutually insoluble and are only slightly soluble. and divided by distinct boundaries. So the principle of manufacture of composite has been borrowed from nature. Trunks and stems of plants are bonded by that trunks and stems of plants and bones examples of natural composites. In wood, cellulose fibers are bonded by plastic lignin. In bones, thin and strong fibers of phosphates are bonded by plastic collagen. Okay, so this is how the manufacture of composites are being done. Okay, then the most important thing that is need to be, you can say, known to us that composite materials are superior to all other known structural materials in specific strength and stiffness, high temperature strength, fatigue strength, and their properties, other properties. Okay, so you can, if you the desired combination of properties, this can be tailored in advance. Okay, so this is very important characteristic of this composite materials. Now the properties of composites, it mainly depends on physiomechanical properties. The properties of composites, it mainly depends on physiomechanical properties of their components and the strength of the bonds between them. Okay, then the strength of the bond between them. A characteristic feature of composite materials is that the merits of their components are fully utilized. What they say, the feature of this composite material is that the merits of the components are fully utilized. You can see in this diagram also the properties of the first reinforced movement material and the matrix inside the second material. We can see the properties, the features are combined in the composite. Okay, so the composite materials may acquire certain valuable properties not found in the components. Okay, then the base or the matrix of components, the base or matrix of the components may consist of metals or alloys, polymers, carbon, and ceramic materials. So the matrix is essentially the binding and shaping component. What do you say? The matrix is essentially the binding and shaping component in components. So its properties determine to a large extent the process conditions. What they say? Its properties is determine to a large extent the process conditions for the manufacture of composite materials and the important operating characteristics. Example, working temperature, fatigue strength, resistance to environment effects, density, and specific strength. Okay, this is how you can easily understand. Now, composites with combined matrix, it may be called as multi-matrix. What do you call as multi-matrix or multi-layer composites? You can see in this figure, you can see that in the figure A, you have this matrix 1 and matrix 2, and then you can see the arrows are pointing towards them, then you have a fiber. Whereas this is called as a multi-matrix. And in the figure B, you can see that you see the matrix is pointing, the arrows pointing towards the matrix, and then you have figure fiber 1 and fiber 2. So you can see in this clearly the B figure is for polyfiber composite materials. Okay. So composites with combined matrix may be called as multi-matrix or multi-layer composites, and multi-matrix composites, okay, they can be characterized by a wider spectrum of useful properties. Like for example, use of titanium as an addition to aluminium. Aluminum is a very softer material with very low melting point, around 650 degrees centigrade only. It is the melting point of aluminium. And titanium obviously is very high. So titanium as an addition to aluminium may increase the strength of composite material in directions transverse to fibers. In direction transverse to fibers. So aluminum layers inner matrix diminish the density of composite materials. Okay. Now fillers. So let's go to fillers. Other components are uniformly distributed in a matrix. These play the major part in strengthening of composites and thus they are called strengtheners. So fillers should possess high values of strength, hardness, and elastic modulus. These fillers that should possess high values of strength, hardness, and elastic modulus. So these characteristics should be substantially higher than those of the matrix, and with an increase of the elastic modulus and ultimate strength of a filler, the corresponding properties of a composite material also increase, but do not reach the value of the filler. The fillers, these are alternatively called reinforcing components. These are called as reinforcing components. This is a broader term than strengthener. It does not specify the particular strengthening role of the filler, but which may used for improving other properties of the components of the composite. Sorry, may be used for improving other properties of composite. The properties of a composite material may also depend on the shape, that is the geometry, dimension, concentration, distribution of filler, that is the reinforced pattern. So as regards their shape, fillers are classified into three main groups. That is, one is zero dimensional, one is one dimensional, and the third is two dimensional. So by reinforcement pattern, composite materials are divided into three groups. That is the uniaxial, biaxial, and triaxial reinforcement. So the main thing you can, if you remember about fillers, they say that the properties of a composite material also depend on the shape, that is the geometry, dimensions, the concentration and distribution of the filler. Okay, so this is how they do. Now next slide. Now fillers of different shape may be used for obtaining a wider complex of properties or enhancing a particular property of a composite material. Okay, you can use this filler, you can use as a, you can say, to obtain certain properties or enhancing particular property of a composite material, like for one dimensional strength, glass, or for one dimensional filler elements. Uh, okay, so you can say that, for example, the strength of bond between one dimensional filler elements, glass or carbon fibers, and this can be increased by introducing a zero dimensional figure, particles of asbestos, silicon, carbide, etc. Okay, what they say that you can use fillers of different shape. It may be used for obtaining a wider complex of properties, for enhancing a particular property of a composite material. So for example, the strength of bond between one dimensional filler element like glass or carbon fibers and a polymer matrix can be increased by introducing a zero dimensional filler like particles of asbestos, silicon, carbide. The same purpose may be achieved by reinforcing a composite materials with fillers of the same shape but different composition. So, for example, the modulus of elasticity of composite materials with a polymer matrix reinforced by glass fibers. Okay, reinforced by glass fibers. This may be increased by additional reinforcement with boron fibers. Okay, what to say? For example, the modulus of elasticity in this, the modulus of elasticity of composite materials. Okay, the modulus of elasticity of composite materials with a polymer matrix reinforced by glass fibers may be increased by additional reinforcement with boron fibers. So composite materials containing two or more different fillers are termed as complex reinforced composites. You can see this in the figure B, polyfiber composite materials. Okay, this diagram that we have seen in the previous slides also, the schemes of multimatrix and polymer of composite materials. Now, particle reinforced composites. Now, these are for classified into two subgroups like large particles and dispersion strength composites. So, the distinction between these this is based upon the reinforcement or strengthening mechanism. We say the distinction between these is based the distinction between These is based on upon reinforcement, right? The distinction between these is based upon reinforcement or strengthening mechanism. So this term large indicate the particle matrix interactions. It cannot be treated on the atomic or molecular level. Rather, continuum mechanics is used. Okay, so we say the distinction between this is based upon reinforcement or strengthening mechanism. Okay, so here the term large is indicated that particle matrix interaction cannot be created on the atomic or molecular level. So the particulate phase for most of these composites is harder and stiffer than the matrix. The particulate phase for most of these components is harder and stiffer than the matrix. So in the vicinity of each particle, okay, what they say, in the vicinity of each particle, these reinforcing particles then tends to restrain movements of the matrix phase. Like if you talk about this, in the diagram, you can see that we have large particles in the matrix, and then you have nano-sized particles in the matrix. This is how they look like. Okay, and they say that this particulate phase, okay, for most of these composites is harder and stiffer than the matrix. That is important. Now, obviously, the matrix transfers some of the applied stress to the particles, which bears fraction of the load. Which okay, the degree of reinforcement or improvement of mechanical behavior it depends on strong bonding at the matrix particle interface. So particles for dispersion, strength, and composites are normally much smaller, that is diameter between zero point zero 0.01 to zero point 0.1 mm, and particle matrix interactions occur on the atomic or molecular level and lead to strengthening. Okay, this particle matrix interactions these occur on the atomic or molecular level and lead to strengthening. So the matrix bears the major portion of the applied load, whereas this small dispersed particle hinder or impede the motion of dislocation. Obviously, when you talk about this, the plastic deformation is restricted such that the yield and tensile strength as well as the hardness improve. Okay, the main thing is that the matrix here it bears the major portion of the applied load, whereas the small dispersed, you can see this in the diagram, particles hinder or impede the motion of dislocation. This is how it works. So fiber reinforced composites. So these are strong fiber embedded in a softer matrix to provide strength to weight ratios. So the matrix material transmits the load to fibers, which absorbs the stress. And under an applied stress, the fiber matrix bond increases at the fiber ends, yielding a matrix deformation pattern. What happened? The matrix material it transmits the load. What happened? The matrix material it transmits the load to fibers which absorbs the stress. So under an applied stress, this fiber matrix bonds this at the fiber ends, yielding a matrix deformation pattern. So in order to have effective strengthening and stiffness of the composite material, some critical fiber length is essential. This critical length, that is called short form as LC, is dependent on the fiber diameter, that is small d, and its ultimate or tensile strength, and on the fiber matrix bond strength. So you can see in the diagram also you have this unidirectional, bidirectional, discontinuous fiber and woven phase shown to you. Now the strength of these composites comes from the bonding between the reinforcement fiber and the matrix. So the length to diameter or aspect or ratio of the fibers used as reinforcement influences the properties of the component. What they say? The length to diameter is reinforces, such as influences. Okay, the higher the aspect ratio, the stronger the composite. Okay, the higher the aspect ratio, the stronger the composite. Therefore, long continuous fibers are better than short ones for composite construction. Therefore, long continuous fibers these are better than short ones for composite construction. However, continuous fibers are more difficult to produce and place in the matrix. Okay, continuous fibers these are more difficult to produce and place in the matrix. The short fibers are easier to place in a matrix. The short fibers these are easier. Okay, when you talk about short fibers, these are easier to place in the matrix but offer poor reinforcement. Okay, now here it is saying that the continuous fibers are difficult to produce, but shorter fibers are easier to place in the matrix. The greater the number of fibers, the stronger the composite. This holds true up to about 80% of the volume of the composite, whereas the matrix can be no longer completely surrounded the fibers. So the one thing is important: the length to diameter or aspect ratio of the fibers, which are used as reinforcement, it influences the properties of the composite. The higher the aspect ratio, the stronger the composite. Okay, let's talk about fibers. Okay, now the fibers for which this is L is greater than LC normally around the value given are called continuous, whereas fibers which have lengths shorter than this are termed as discontinuous. So the matrix deforms around the continuous fiber having length less than LC such that there is a virtually no stress into transference and little reinforcement by the fiber. So in order to effect a significant improvement in the strength of the composite, the fibers must be continuous. The arrangement or orientation of the fibers relative to each other, the fiber concentration and distribution all have the significant influence on the strength and the properties of the fiber reinforced composites. So here also you can see in the diagram on the bottom side, you can see the representation of the first is A is the continuous and aligned. You can see there you have a direction also shown to you. The second in the B you have discontinuous and aligned. And the third you have discontinuous and randomly oriented fiber reinforced composites. Okay. You can clearly see in these diagrams are a very good example of how it is shown. So there are two possible extremities with respect to the orientation. Like one is the parallel alignment in the longitudinal axis of fibers in a single direction. Second, a total random alignment. What to say? A total random alignment. That is, continuous fibers are normally aligned as shown in this figure. Discontinuous fibers may be aligned also as shown in the figure B and randomly oriented. You can see in the figure C. Okay, so one can realize overall better composite properties when fiber distribution is uniform. Okay, one can realize overall better composite properties. Okay, when fiber distribution is uniform. Okay, so you can do this. Now you can see this diagram very clearly shown to you. Well, let's start with the MCQs now. Okay, the MCQs are also very important for this. Right, the first MCQ. So in this first MCQ, on the basis of diameter and character, on the basis of diameter and character, the fibers are grouped into three different classifications like whiskers, fibers, and wire. So what I think is true or false? I think it's true. Now whiskers are very thin single crystals that have extremely large length to diameter ratio. So the consequence of their small size, they have a high degree of crystalline perfection. What? They have a high degree of crystalline perfection and are virtually flaw free, which accounts for the exceptionally high strength. Okay. As a consequence of their small size, they have a high degree of crystalline perfection and are virtually flaw free, which accounts for their exceptionally high strength. They are among the strongest known materials. So it is true or false. So I think if you talk about in detail, I think they have extremely large length to diameter ratios. I think it's true. The answer is A. They have these, you can say, the statement is true. They have extremely large length to diameter ratios. This was true. A is the answer. In spite of these high strength, this are not utilized extensively as a reinforced medium because they are extremely expensive. True. A is the answer. Now, fibers are either polycrystalline or amorphous and have small diameters. The fibrous materials are generally either polymers or ceramics. And the examples they have given like glass, carbon, boron. So I think it's true. Aluminum oxide, silicon carbide. The answer is true. A is the answer. Okay, we know this. These are either polycrystalline or amorphous. Okay, and the examples are also true. Like aluminum oxide, silicon carbide. A is the answer. True. Okay. Fine wires that have relatively large diameters. Typical materials include steel, molybdenum, and tungsten. So wires are utilized as a radial steel reinforcement in automobile tires and filament-bound rocket wire casings and in wire-bound high-pressure hoses. So we have discussed this also in detail during our lecture. So I think it's true in this case. A is the answer. A composite is considered to be any multi-phase material that exhibits a significant proportion of the properties of both constituents phases, such as a better combination of properties is realized. So this is termed as the principle of combined action. What we call as we term this as principle of this combined action. Okay. When you say this principle of combined action, so I think it's true. You can say a composite compose is considered to be a multi-phase material that exhibits a significant proportion of the properties of both constituent phases, such that a better combination of properties is realized. So this is termed as principle of combined action. I think it's true in this case. The answer. So all composites generally have one thing in common. Okay, what you say? All composites generally have one thing in common: a matrix or a binder combined with a reinforcing material. True. True is the answer. A is the answer. So reinforced concrete is a good example of composite material. When concrete is reinforced with steel rubber, the concrete becomes matrix. It surrounds the reinforcing fiber, the rubber. Okay, reinforced concrete is a good example of composite materials. And when concrete is reinforced with steel rubber, the concrete becomes the matrix. It surrounds the reinforcing fiber, the rubber. The rubber. So what do you think? True. True is the answer. A is the answer. One can classify composite materials as simple scheme. These are three main divisions like particle reinforced, fiber reinforced, and structural composites. I think these divisions are like okay. Particle reinforced, fiber reinforced, and structural composites. We have discussed the whole chart. Okay, so I think it's true. A is the answer. The incorporation of fibers into brittle ceramics produces a composite of enhanced toughness. So fillers such as the presence of aggregate in concrete reduce the overall cost of the product and additionally improve the compressive strength. So I think it's true. This A is the answer. The incorporation of fibers into brittle ceramics produces a composite of enhanced toughness. Okay, so I think it's true. A is the answer. So these are the references which you can refer and obviously increase your knowledge in these topics. So thank you very much.